To determine the appropriate conduit size, a conduit fill calculation is necessary. This calculation helps ensure that the conduit is not overcrowded with conductors, which could lead to overheating and potentially hazardous conditions. The National Electrical Code, or NEC, provides guidelines and formulas for calculating conduit fill. The fundamental formula for conduit fill percentage is number of conductors multiplied by conductor area, divided by the conduit cross-sectional area, all multiplied by 100. We can find useful information in NEC section 314.16a on. Let's apply this to the provided scenario. First, we need the conductor area. For number 12 THHN wire, the conductor area is 0.62 square inches. Second, the number of conductors in this example is 9, accounting for the 420 amp receptacle circuits, each with 2 current carrying conductors plus 1 ground wire. Because the ground has been daisy chained, there is only 1 ground wire. Third, the conduit cross-sectional area. For a 3/4 inch rigid metal conduit, or RMC, the cross-sectional area is 0.44 square inches. Now, we can calculate the conduit fill percentage. The fill percentage is equal to 9 multiplied by 0.62 divided by 0.44 multiplied by 100, which equals 13.9%. Next, consider derating for conduit fill. NEC Table 310.15b3 provides derating factors for conduit fill percentages above 40%. Since the calculated conduit fill percentage is 13.9%, which is less than 40%, no derating is required. Based on these calculations, a 3/4 inch conduit is sufficient for the 9 number 12 THHN wires, including the ground. No derating is needed in this specific scenario. The NEC specifies the maximum allowable fill percentages for different types of conduits. These percentages are designed to ensure adequate space for heat dissipation and to prevent damage to the conductors during installation and operation. For more than 2 wires, the fill percentage is limited to 40%. When the conduit fill exceeds these limits, the ampacity of the conductors must be derated according to NEC Table 310.15b3. This table provides adjustment factors based on the number of current carrying conductors in the conduit. Derating reduces the allowable ampacity of the conductors to prevent overheating. To use NEC Table 310.15b3, you first determine the number of current carrying conductors in the conduit. Then find the corresponding adjustment factor in the table. Multiply the conductor's ampacity by the adjustment factor to obtain the derated ampacity. For example, if you have 7 to 9 current carrying conductors in a conduit, the adjustment factor is 70%. If the original ampacity of the conductor is 30 amps, the derated ampacity would be 30 amps multiplied by 0.7, which equals 21 amps. Always consult the latest edition of the NEC for the most up-to-date requirements and tables. The NEC is regularly updated to reflect changes in technology and best practices. Understanding and applying conduit fill calculations and derating factors is essential for ensuring safe and compliant electrical installations. Proper conduit fill prevents overheating and potential fire hazards, while correct derating ensures that conductors are not overloaded. By following these guidelines, electricians can create reliable and safe electrical systems. In summary, to calculate conduit fill, use the formula conduit fill percentage equals the number of conductors multiplied by the conductor area, divided by the conduit cross-sectional area, all multiplied by 100. Check NEC Table 310.15b3 to determine if derating is required based on the number of current carrying conductors. If the conduit fill percentage is less than 40%, no derating is needed. If the conduit fill percentage exceeds 40%, use the appropriate adjustment factor from the table to derate the conductor ampacity. By following these steps, you can ensure a safe and compliant electrical installation. Let's delve deeper into each aspect of conduit fill calculations and derating, providing a comprehensive understanding of the principles and practices involved. Firstly, conductor area is a critical factor in determining conduit fill. The area of a conductor depends on its size and type. The NEC provides tables that list the cross-sectional area of various types of conductors. For example, number 12 THHN wire has a cross-sectional area of 0.62 square inches. It is essential to use the correct conductor area for accurate conduit fill calculations. Secondly, the number of conductors in a conduit is another key factor. This includes all current carrying conductors, as well as any equipment grounding conductors or bonding jumpers. Neutral conductors are also counted as current carrying conductors under certain conditions, such as when they carry significant harmonic current. It's important to accurately count all conductors to ensure the conduit is not overfilled. Thirdly, conduit cross-sectional area varies depending on the size and type of conduit. The NEC provides tables that list the internal cross-sectional area of different types of conduits, such as rigid metal conduit, electrical metallic tubing, and flexible metal conduit. It's important to use the correct conduit area for accurate conduit fill calculations. Now let's discuss derating in more detail. Derating is the process of reducing the allowable ampacity of conductors when they are installed in conditions that limit their ability to dissipate heat. This is necessary to prevent overheating and potential fire hazards. The NEC provides derating factors based on the number of current carrying conductors in a conduit, as well as the ambient temperature. When multiple current carrying conductors are installed in a conduit, they generate heat that can raise the temperature inside the conduit. This reduces the conductor's ability to dissipate heat, and its ampacity must be derated accordingly. The NEC Table 310.15b3 provides adjustment factors for different numbers of current carrying conductors. For example, if there are 4 to 6 current carrying conductors in the conduit, the adjustment factor is 80%. This means that the conductor's ampacity must be reduced by 20%. In addition to the number of conductors, ambient temperature also affects the ampacity of conductors. The NEC provides correction factors for different ambient temperatures. If the ambient temperature is higher than the conductor's rated temperature, its ampacity must be derated. For example, if a conductor is rated for 90 degrees Celsius and the ambient temperature is 40 degrees Celsius, no temperature correction is necessary. However, if the ambient temperature is 50 degrees Celsius, the conductor's ampacity must be derated using the appropriate correction factor from the NEC. Let's consider some examples to illustrate these principles. Example 1. Suppose you have 6 number 12 THHN wires in a 3/4 inch conduit. The conductor area of number 12 THHN wire is 0.62 square inches. The cross-sectional area of a 3/4 inch conduit is 0.44 square inches. The conduit fill percentage is calculated as follows: 6 multiplied by 0.62 divided by 0.44 multiplied by 100, which equals 8.45%. Since the conduit fill percentage is less than 40%, no derating is required based on conduit fill. However, since there are 6 current carrying conductors, the ampacity must be derated according to NEC Table 310.15b3. The adjustment factor for 4 to 6 current carrying conductors is 80%. If the original ampacity of the number 12 THHN wire is 30 amps, the derated ampacity is 30 amps multiplied by 0.8, which equals 24 amps. Example 2. Suppose you have 10 number 14 THHN wires in a 1 inch conduit. The conductor area of number 14 THHN wire is 0.51 square inches. The cross-sectional area of a 1 inch conduit is 0.864 square inches. The conduit fill percentage is calculated as follows: 10 multiplied by 0.51 divided by 0.864 multiplied by 100, which equals 5.9%. Since the conduit fill percentage is less than 40%, no derating is required based on conduit fill. However, since there are 10 current carrying conductors, the ampacity must be derated according to NEC Table 310.15b3. The adjustment factor for 10 to 20 current carrying conductors is 50%. If the original ampacity of the number 14 THHN wire is 20 amps, The derated ampacity is 20 amps multiplied by 0.5, which equals 10 amps. Example 3. Suppose you have 3 number 10 THHN wires in a 1/2 inch conduit and the ambient temperature is 45 degrees Celsius. The conductor area of number 10 THHN wire is 0.87 square inches. The cross-sectional area of a 1/2 inch conduit is 0.304 square inches. The conduit fill percentage is calculated as follows: 3 multiplied by 0.87 divided by 0.304 multiplied by 100, which equals 8.58%. Since the conduit fill percentage is less than 40%, no derating is required based on conduit fill. Since there are only 3 current-carrying conductors, no derating is required based on the number of conductors. However, since the ambient temperature is 45 degrees Celsius, the ampacity must be derated according to the NEC temperature correction factors. Assuming the conductor is rated for 90 degrees Celsius, the correction factor for an ambient temperature of 45 degrees Celsius is approximately 0.91. If the original ampacity of the number 10 THHN wire is 35 amps, the derated ampacity is 35 amps multiplied by 0.91, which equals 31.85 amps. In summary, conduit fill calculations and derating are essential for ensuring safe and compliant electrical installations. Always use the correct conductor area and conduit area for accurate calculations. Consult NEC Table 310.15b3 for derating factors based on the number of current-carrying conductors. Also consider ambient temperature and apply the appropriate correction factors. By following these guidelines, electricians can create reliable and safe electrical systems. Now let's address some common misconceptions about conduit fill and derating. Misconception 1 is that conduit fill is only about the physical space inside the conduit. While physical space is important, conduit fill calculations are also about heat dissipation. Overfilling a conduit can restrict airflow and prevent conductors from dissipating heat effectively, leading to overheating and potential fire hazards. Misconception 2 is that derating is only necessary when the conduit is completely full. Derating is required whenever the number of current-carrying conductors exceeds 3, regardless of the conduit fill percentage. Even if the conduit is only partially full, the heat generated by multiple conductors can raise the temperature inside the conduit and require derating. Misconception 3 is that derating is always a fixed percentage. The derating factor depends on the number of current-carrying conductors and the ambient temperature. The NEC provides specific adjustment factors and correction factors that must be used to determine the appropriate derating. Misconception 4 is that derating is not necessary for short conduit runs. Derating is required regardless of the length of the conduit run. Even in short conduit runs, the heat generated by multiple conductors can still raise the temperature inside the conduit and require derating. Misconception 5 is that derating is only necessary for power circuits. Derating is required for all types of circuits, including power circuits, lighting circuits, and control circuits. Any circuit with more than 3 current-carrying conductors and a conduit must be derated according to the NEC. Now let's discuss some practical considerations for conduit fill and derating. First, always use the correct size conduit for the number and size of conductors you are installing. Using a conduit that is too small can make it difficult to pull the conductors and can also restrict airflow, leading to overheating. Second, when installing multiple conductors in a conduit, try to arrange them in a way that maximizes airflow. This can be achieved by staggering the conductors or using cable ties to keep them separated. Third, when derating conductors, be sure to use the correct adjustment factors and correction factors from the NEC. Using the wrong factors can result in an unsafe installation. Fourth, when in doubt, it is always better to over-deret than to under-deret. Over-derating will reduce the conductor's ampacity, but it will also increase the safety margin. Under-derating can lead to overheating and potential fire hazards. Fifth, always consult with a qualified electrician if you have any questions or concerns about conduit fill or derating. A qualified electrician can help you determine the correct conduit size, derating factors, and installation practices for your specific application. In addition to these practical considerations, it is also important to be aware of local codes and regulations. Some jurisdictions may have additional requirements for conduit fill and derating that are more stringent than the NEC. Always check with your local authorities to ensure that you are in compliance with all applicable codes and regulations. Furthermore, consider the future needs of the electrical system when planning conduit fill. If there is a possibility that additional conductors will need to be added to the conduit in the future, it is best to use a larger conduit size to accommodate these future needs. This can save time and money in the long run by avoiding the need to replace the conduit later. Moreover, proper labeling of conduits is essential for maintenance and troubleshooting purposes. Label each conduit with the circuit number, conductor size, and derating factors. This will help electricians quickly identify the conductors and derating requirements, making it easier to maintain and repair the electrical system. In conclusion, conduit fill calculations and derating are critical aspects of electrical installations. By understanding the principles and practices involved, and by following the guidelines and requirements of the NEC, electricians can create safe, reliable, and compliant electrical systems. Remember to always use the correct conductor area and conduit area for accurate calculations. Consult NEC Table 310.15b3 for derating factors based on the number of current carrying conductors. Also, consider ambient temperature and apply the appropriate correction factors. Be aware of common misconceptions and practical considerations, and always consult with a qualified electrician if you have any questions or concerns.